right, this is section 7.2, and now that we've kind of got a pretty good idea of how to simplify our radicals, we're now going to talk about doing operations on them. That is, how do we add, subtract, multiply, or divide with radicals? So we'll start with adding and subtracting. And the rule for adding and subtracting is you can only do it if you have like radicals. What do we mean by like radicals? Well, like radicals have the same index and the same radicand. So let's see. Well, there's a little vocabulary in there. Let's talk about that. If I have the nth root of something in here, the index refers to that little number there, the root that I'm taking, the third root, the fifth root, whatever. And the radicand refers to whatever it is that's underneath my radical sign. Those all have to be the same if we're going to have like radicals. So for example, here, they're both square roots, and the radicand is 6x for both of them. So these are like. Both square roots. Both have the same radicand, 6x. All right, what about this next one? Well, they're both fifth roots, so the index is the same. And what's underneath, the 2x squared y, is also the same. So these again are like radicals. The same index, which is 5. Technically, the square roots, by the way, have the index of 2. We just don't usually bother writing the 2 with the square root, right? So here the index is the same, it's 5. And they both have the same radicand. It is 2x squared y. All right, take a look at this next one. Although they're both square roots with an index of 2, the radicands are different. This has got the 5 and that's got the 7 with the AB. So these are unlike because they have different radicands. And here the radicands are the same, but this time the index is different. That's a cube root and that's a square root. So these are also unlike. They have a different index. All right, so let's suppose now we understand when we can and can't. We know we need like radicals. If we have like radicals, here's what we do to add or subtract them. First of all, make sure all your radicals are simplified. Sometimes we won't recognize the like radicals until we see the simplified forms. And then we can combine those like terms by adding or subtracting just the coefficients of the like radicals. So in my first example, I'm going to look at that and say, well, I think I probably could break those down a little bit, simplify. 72. When I'm thinking about a perfect square that goes into 72, I'm thinking 36 times 2. Right, 36, nice perfect square there. And then the n will have to go over here. So that'll give me 6 square root 2n. Plus, I'm going to break down the square root of 18n. And again, I want a perfect square that goes into 18. So I'm thinking about 9. 9 times 2. And the square root of n is not going to come out evenly. So I'm really adding 3 times the square root of 2n. Now notice those are like radicals, so it's okay to add them. I do that by adding the coefficients. 6 plus 3 would give me 9 times the square root of 2n. All right, what about part B? Lots of radicals to simplify here, so let's work on that first. Square root 20 I'm going to go with 4 and 5 would give me 2 square root 5 minus 3 times. Looking at that 63, 9 goes into that, so let's go with 9 times 7. I got 3 times the square root of 9. That's really 3 times 3, which would be 9 times the square root of 7, minus 5 times, and I'm looking at that 180. I think 36 goes into that. Let's just check. Yes, 36 times 5. So minus 5 times 6, right? Square root of 36 is 6. So 5 times 6 is 30. Square root of 5. And I got one more, plus square root of 700. I'm going to go with 100 times 7. So that would be plus 10 times the square root of 7. Whew, a lot of simplifying there. All right. Those are like radicals. They both have a square root of 5, so it's okay to combine them. 2 minus 30 would give me negative 28 times the square root of 5. And then these are also like radicals. Okay, they both have a square root of 7. So I'm going to go negative 9 plus 10 would be plus 1 times the square root of 7. Can't combine those anymore. They're not like radicals, so I'm done. All right, a couple more like that. In part C, we're going with cube roots this time. Again, right now they don't look like radicals, but I haven't simplified them yet, so we'll see. On this first one, cube roots now, so think perfect cubes that go into 128. And I think 64 times 2 would be a good way to go there. And then I look at the x's. So with those x's, let's see, I need them to be the power to be divisible by 3. So the closest I'm going to come there would be x to the 6th, with the extra x to the first over here. The cubed root of 64 is 4, and dividing the exponent by 3 gives me x squared. And then I still have a cubed root of 2x. All right, to that I am adding x times, and again I'm going to break this down if I can. 16. Best perfect cube that goes into 16 would be 8. So I'm going to go with 8 times 2. And I'll split that up as x to the 3rd times x to the 1st. So this is really x multiplied by 2x to the 1st. That's 2x squared. And then I've got a cube root of 2x left over. All right, are these like terms? Well, the variables outside the radical match, so that's a good sign. They're both cubed roots, same index, and the radicand is the same. So yes, these are like radicals. I can combine them by adding the coefficients. 6x squared times the cubed root of 2x. All right, I have one more adding and subtracting problem for us over here. And as I look through here, I don't think there's anything that I can actually simplify this time. So this time it's just going to be a matter of looking for those like radicals. I'm actually going to start out with the constants. I've got positive 4 and negative 1. So that would give me 3. I guess they're all technically constants. There's no x's here, but the whole numbers, let's say. And then the other like radicals are going to go because of the index. These all have 4 as the radicand, but those two have the same index. They're both cubed roots. So I'm thinking 3 cubed roots of 4 plus 1 cubed root of 4 would be plus 4 cubed roots of 4. These guys are also like terms or like radicals because they both have the same index of 4. So once again, I'm going to combine those. I combine my coefficients, negative 6 and negative 8 would be negative 14 times the 4th root of 4. None of these are like terms anymore. These have different index. So that's as good as it gets. All right, so that's adding and subtracting. You have to have like radicals to do it. What about multiplying? Well, it turns out you can actually multiply any radical as long as it has the same index. So no need to worry about the radicands matching, just the index has to match in order to multiply. You should always simplify after you multiply like we've been doing, remove any perfect nth powers, and keep a couple of tips in mind. Basically, I say outsides with outsides, numbers outside the radical, multiply other numbers that are outside, and then insides with insides. Also watch for common multiplication strategies that we've seen before, things like distributive laws and FOIL, the kinds of things that you're already familiar with for multiplication are probably going to crop up again here. So let's get started. In example 2a, I am multiplying these together. So I just multiply the outsides, negative 18. And then under the square root, I multiply these guys, 48x squared. To finish this, I'm going to try to simplify my radical. So let's see if I can break it down. 48, I could break down as 16 times 3. Right? 16 is a nice perfect square. And the x squared is already going to be fine, so I'll leave it here. So I have negative 18 times 4x to the first times the square root of 3, or negative 72x times the square root of 3. All right, let's take a look at B. This 3 is outside these parentheses, so I'm thinking that 3 is going to be a distributive law. And the same with that 5. Distributive law there as well. So here, the 3 is outside. I can't put it into the inside of the radical, so it's going to be 3 times the square root of 2x. That's going to give me a negative 12 times the cubed root of 2x. And over here, a plus 15 times the cubed root of 2x. And finally, a negative 30 times the square root of 2x. All right, all the radicands are the same, but I do have a couple of different indexes, right? Or indices, technically, is the plural, I guess. A couple cube roots and a couple square roots. So let's combine the square roots first. 3 minus 30, so negative 27 square root 2x. And then the other two terms are also like terms because they're both cubed roots. of 2x, negative 12 and plus 15. So plus 3 times the cubed root of 2x. And because those are no longer like radicals, I cannot add them. I can't combine them any further. And I'm done. All right, a couple of more problems in multiplication for us here at the top of page 313. If you look at C, I'm hoping that reminds you of a strategy that you've already used in this class. This is a binomial and that's a binomial. When we multiply two binomials, we typically either use FOIL, if you used it or learned it that way, right? First, outer, inner, last. Or sometimes people just think of it as two distributive laws. So my firsts would be 2 times the square root of a squared. Now if you're thinking, wait a minute, that's just a. Of course, you're absolutely right. I'll be simplifying that in my next step. Outer, negative 6 square root of a times b. Inner, plus there's just 1 on the outsides, but that'll also be the square root of a times b on the inside. And then the lasts, negative 3 square root of b squared. All right, those two can of course both be simplified. The square roots come out evenly. And then I can combine the like terms in the middle here. Negative 6 square root ab plus 1 square root ab. So I end up with 2a, negative 5 square root ab, and then minus 3b. No more like terms, so that's done. D is basically the same process. Remember that when you square something, it just means to multiply it by itself. So if I write it out that way, that just becomes two distributive laws, or FOIL again. So I'm going to start with 16 square root of 9w squared. And then negative 20 square root 3w. And then another negative 20 square root 3w. And then a plus 25. All right, that's really 16 multiplied by 3w to the first. So that's really 48w. These are like terms, like radicals there, so they can be combined. Negative 40 square root 3w. And then that plus 25 just comes on down, nothing I can really do to change that. No more like terms, and so we're done. All right, when we started here, I said that you can multiply radicals as long as they have the same index, right? They're both square roots, or they're both cube roots, or something like that. In fact, there is a way to get around that, but I can't do it with radicals. If I really need to multiply radicals with different indices, I have to convert them to exponent notation, and then I'll be able to multiply just using my rules of exponents. So what would that look like? Different indices means I can't multiply them as radicals. So I'm going to write this as x to the 1/4 power multiplied by x to the 1/6 power. And now to multiply, I know that I have to add exponents. If you don't want to do that by hand, you certainly can add them on Desmos or on your calculator. 1/4 plus 1/6 and then just use my math menu to change that to a fraction, is 5/12. Typically, when we have problems, we usually like to give our answer in the same notation as the original problem. So since we started with radicals here, I'd probably give my final answer as a radical also. This is x to the 5th power, the 12th root. All right, let's try that again. I noticed right away that 5th root and square root are going to have different indices. So I'm going to rewrite that as 2 times n to the 1/5 plus n to the 1/2. And squaring it means to multiply it by itself. All right, when I multiply here, I'm going to get 4. And then when I add those powers, 1/5 plus 1/5 makes that n to the 2/5. Multiplying here, 2 times 1 is a plus 2. And then I have to multiply, so I'm really adding the exponents. 1/5 plus 1/2. Again, if you want to just use your calculator to do that, you certainly can. That is 7/10. Again, Desmos is fine as well. All right, inners, really the same exact thing, right? Plus 2, and then I'd add the 1/2 plus 1/5, which I just did, so n to the 7/10 plus n to the 1/2 times n to the 1/2 is technically n to the 2/2 when I add the powers. Of course, that's just going to be n to the 1st, right? All right, we're almost there. 4n to the 2/5 plus, I'm going to combine those like terms, 4n to the 7/10 plus simply n to the 1st. And last step here, once again, the original problem was stated with radicals, so I probably would like to give my final answer in radical form as well. I have 4 times the 5th root of n squared plus 4 times the 10th root of n to the 7th plus n. All right, we've added and subtracted, we've multiplied. Last thing we have to talk about is division. And really, division in the case of radicals is going to consist of just simply separating any fraction that's under a radical, it's that quotient property, and then simplify your result. Simplify the top, simplify the bottom. So what is that going to look like? Well, here I've got 2, and the top would be the square root of 5. I'm going to separate the square root of 12 on the bottom as its own radical. 2 times the square root of 5, nothing I can do about that. That's as simple as it's going to get. But I can break down the denominator a little bit. Let's see, a perfect square that goes into 12 would be 4. So let me break that down as the square root of 4 times the square root of 3. That's 2 times the square root of 3. And in this case, I can divide out those 2's. So I just end up with the square root of 5 over the square root of 3. Before I leave that problem, I'm just going to mention the note at the bottom here. In past algebra classes, You might have been taught that you couldn't leave square roots in the denominator. You had to do something called rationalize the denominator. You are not required to do that in this course. It's not that it's wrong, and if you've learned it in the past and like to do it, it's fine, but you do not need to. Okay? It's kind of an archaic thing in a lot of ways. The purpose of rationalizing denominators was because it made calculations easier with a slide rule. I don't know when the last time any of you used a slide rule was, but I'm thinking that with Desmos and calculators, we don't really need to worry so much about slide rules. So there's no particular reason to worry about rationalizing denominators. And I'll tell you, you're going to go on, and if you go on and take calculus, your calculus teachers are going to tell you they don't care about it either, and just to leave the radicals there. So we're just going to go ahead and start now. No need to worry about it. All right, I have one more division in B here. And this time the 6 isn't under a radical at all, so I'm just going to leave it alone. And then I'm going to see if I can break down the denominator at all. Now I need a perfect cube that goes evenly into 16. They get 8, so let's go with 8 and 2. And that x squared, that's not big enough to have a cube root in it, so I'll just leave that over here. Cube root of 8 is 2 times the cube root of 2x squared. 6 divided by 2 would be 3, divided by the cube root of 2x squared. And again, for the purposes of this class, you are simply going to leave it that way. All right, that brings us to the end of 7.2.